So our next speaker is Shailesh Lal, who is going to tell us about machine learning solutions to the Yang Baxter equation. Please.
Thank you. Is this audible? Does it? Is that okay? I'm guessing that's a yes. Yeah. Okay. So let me begin by thanking the organizers for giving me the opportunity to speak here, and also for putting together this very interesting conference. I'll be talking about work done with Suvajit Majumder and Evgeny Sobko, both of whom are or should be in the audience. So this is actually an oriented talk. So there's a preferred direction. The talk comes from here, but the questions go over there. So okay. So I'd like to tell you about this work which we did about machine learning solutions to the Yang Baxter equation. But the talk is not really as much about the solutions themselves as why it is a good idea in general to think about neural networks if you're searching for solutions. And essentially the talk is about that and how you might want to be doing it. So in a sense, the first, I don't know how much of the talk is really purely pedagogical. If it isn't, it should be, and please stop me and ask. Yeah. Okay. So what is artificial intelligence? Let me just stand up here, actually. So what is artificial intelligence? So as usual, it's better to show rather than tell. So let me tell you about this little quote over here. It's by Marvin Minsky, and it's the science of making machines do things that would require intelligence done by humans. And for the purposes of the talk, I will assume that solving problems in mathematical physics is a sign of intelligence. Okay, so I was looking. So a previous version of this slide actually had this quote: "Artificial intelligence is when a machine does something which, if a human were to do, would be considered intelligent." And I was looking for the attribution, and I couldn't find it anywhere. I put it into Google; it just didn't work. So finally, I asked ChatGPT. I said that, "Look, I'm looking for this quote. I have no idea where it came from, and can you just tell me where it is?" So well, it went through quite well. It said that the exact wording may vary, but the essence of the quote is captured in this phrase, which I've written out for you over there. Okay, so so if there's one lesson that we can take away from this, it's that be nice to your language models because they will be your overlords in the future. But if there are two lessons to take away from this, the second one is that that the AI is actually able to pass through multiple layers of context to get to the semantic content of a statement, right? It's saying something, if done by a human, would be considered intelligent. So there are multiple layers of semantics to pass through to get to the actual content of what the statement is, and it is actually able to do that. And for today's talk, of course, at the time when this quote was given, this wasn't so thing, but quite often in popular thought, artificial intelligence now is kind of synonymous with neural networks. And I'm going to abuse that by just really talking about neural networks. Okay. So why artificial intelligence in physics? And there's a kind of an idea that AI or machine learning or data science requires data by construction. And usually the question is that, well, data is the very thing we are after. So how do we use machine learning in the absence of data? What are the interesting problems one might solve? Okay, so so essentially the idea is that it's really a novel methodology of thinking about a system, right? And even if for no other reason, when you know that a new powerful technique has come along, it's very natural to wonder if there are aspects of your own problems that you can use to try and solve it. So let's try and follow our nose over here, and just in contrast to what you do normally, you'd have an algorithm, and you'd say that, look, here's a way of putting my problem onto a computer, and I'm going to solve it iteratively. It'll run in some order time and then give me an answer. And when we use neural networks, for example, we don't really tell the AI what a solution is. we don't necessarily give an example of a solution or really an algorithm to generate a solution, but we tell the AI data about what a solution is, and then we tell it, and then we let it decide how to get there. Okay. And in many cases, this is actually quite competitive or slightly better than conventional methods. And what I'll be talking about today is really a refinement of this idea, which is that rather than telling the AI what the solution is in terms of giving it input-output variables that one is expected to reproduce, we'd give it constraints on the solution instead. Okay, this will become very natural in a moment, but if you wish to fix your ideas, just imagine that I'm thinking of a meromorphic function, and rather than giving it input-output variables that are particular values of the complex parameter, here are the output variables, I just say that here are the poles and the corresponding residues, and here are the branch cuts and the corresponding discontinuities. Right? So those would be the example of, say, constraints that you just declare that those objects are, rather than giving a lot of input-output variables. So that's a good thing to hold on to. Okay, there's an R missing. So let's take inspiration from biological neurons, and really the idea is that behind this is that what a neuron does effectively is that it takes a whole bunch of inputs, and then at least if you try to model it, what seems to happen is that a weighted sum of these inputs is computed and then processed into an output. And this is a really remarkable, simple thing, a simple model which is responsible for really all our perceptions, decisions, and whatnot. So what would be a mathematical version of this? What is called an artificial neuron, where you have some input data in the form of an input vector. You take a weighted linear combination, you act on the weighted linear combination by a function, and then you get an answer, right? And what you need to tune is really when the neuron essentially fires, right? Which means you tune these weights and biases. And if you imagine that this is a step function, then by tuning these weights and biases, you are really controlling when the neuron is firing, right? That would be the simplest model of a neuron. So now onto neural networks. Well, if you have one such neuron, you can have k such neurons. The same thing goes through, and further, since hindsight is 2020, the input variable I can always call A0, and these ZKs I can call Z1, and the AKs I can call A1. So you can write this as the L equal to 1 instance of the following recursion relation. Okay. So what we call this is the first layer of neurons in this network. So, and higher layers are essentially generated by iterating this transformation. Okay. And these set of equations are essentially the simplest modern neural network, which is called a multi-layer perceptron. And of course, other topologies and all are possible, but I'm not going to use them in this talk. So let me just skip past that. Okay. And what I'd really like you to look at is this hierarchical structure where the output of the previous layer is the input of the current layer, and a weighted linear combination is taken, and output is generated, and that would be fed into as the input of the next layer. Right? And this is really a model of how the human brain functions. There are primitive neurons that take in really the raw input coming in from the outside world, and that is processed into outputs, which is then acted on by more and more and more neurons. And that is where the knowledge of all my knowledge of biology ends. Okay, so the same thing can be represented as this set of transformations, where just to draw out those same set of equations as a graph, you have this input layer which is being passed into a set of what are called hidden layers, and so the name is just an artifact, and then you have what is called an output layer, where you actually measure what you expect it to be getting, right? And again, to emphasize for you, the output is a function of the input variables, but the actual function can be tuned by tuning what these W's and the B's are. Okay. And again, just to summarize the connection, here is your your neuron, which is kind of modeled by this object called the perceptron. And this neuron is connected and feeds its output into different other neurons, and then so on and so forth, which is this multi-layer perceptron. So, of course, in practice, one doesn't really try to use biology to mimic a neural network, but it's nonetheless something very useful to hold on to when you try to think about what's really happening here. Is this fine? Okay. So here's the big question: like, why is it that the kind of problems we did in this work, and we are still continuing to do, why is it that they are so appealing to be solved by neural networks? Okay, so here's a very classic problem. Okay, just forget about integrability. This is really taking in shipping locations and trying to predict when your package will reach, right? The kind of thing you might solve for Amazon. So you start with a set of known input-output variables. You have some variables xi, and then you know what your expected outputs are, right? And you're trying to learn this function by tuning these weights and biases of the neural network so that you are approximately correct most of the time. Okay, that's the rough idea. You don't want to be correct all the time because there could be random fluctuations, and you don't want to model noise. But this is the rough idea of what you're trying to do in this entire machine learning setup. And the claim is that neural networks are universal approximators. And what that boils down to is the claim that whatever data you have, again, I'm being generous with my claims here, but whatever data you have can always be modeled by some neural network. So if I'm suitably generous with always and suitably generous with some, okay? And this is really for two reasons. One, the neural network is wide. There are multiple neurons in a given layer. And the second, that it is deep. So you have multiple such layers, this hierarchical structure, right? So, and in fact, what it will turn out is that if you have infinite number of neurons in a given layer, that itself is enough to learn any data you want, or at least to mimic any data you want. But for various reasons, it's actually a very important thing in theory and in practice to have depth as well. So here's an extreme example of this case, which I'm just going to sketch out some plausibility arguments for you. So an extreme example is that this nonlinearity is actually a step function, right? The baby example for neuron. As soon as the weighted sum reaches a particular threshold value, which I've taken to be 0, it'll fire, right? It'll go from 0 to 1. And this, of course, can be realized as a very limiting case of the tan hyperbolic. So, and in this limit, I would like to claim that whatever function you have can always be modeled by some neural network or the other, right? And of course, then it's clear what you have to do. You know that such a function, at least in this baby 1D example, there would be a histogram approximation, right? So if you can learn the histogram, then you've proved the theorem, at least at the level of rigor that I'm working at, right? So, and of course, the finer the number of bins, which means the larger the number of bins, the better would be the approximation, right? So if you have the step function, then you could take a linear combination of the step function to write down something that fires at a threshold value, but after the next threshold value, you subtract out another step function, and then it becomes 0 again, right? And then that you can multiply by any number that you choose, and you have this bin. And well, once you have one bin, you can add up all of them, and then you see that any such, this is for multiple dimensional input, but if you had a single dimensional input, you could essentially put together all these weighted sums, and every adjacent neuron would correspond to, a pair of neurons would correspond to one such bin, and there you'd have your proof. So that's basically the idea of why a single neuron with an infinite number of a single neural network with a single number of infinite and with a single infinitely wide hidden layer is actually a universal approximator. Okay. So, well, if this is the case, then why do we need depth? And the idea is that depth is really crucial to learning hierarchical structures. Right? So, and the prototypical example of that is actually this kind of a sawtooth wave function. So if you have a function like this, you could compose it and you'd get two peaks, and then compose it again, you get these and this, and so on, right? But so you could say that, well, if I'm going to use my neural network to this kind of a histogram approximation, or this kind of a peaked activation, then I really need just one peak to describe this. So I need one neuron. I need two peaks to describe this, so 2, 4, and 16. But if I notice that this is really the function of a function, then I don't really need to arrange all of these peaks and as a single wide layer. I can do it by composing that activation function, and I have much fewer neurons that I need. But more importantly, it's not just memorizing the fact that there are these peaks, right? So it would actually be boiling down to learning that there is this hierarchical structure that's repeating again and again and again, and that structure is really responsible for all of these regularities that we are seeing. So it's really learning something about the data and not just memorizing input-output variables. Okay. Yes.
So practically, how do you tell the difference between learning and memorization? You have a trained network. How do you know that it's learned or memorized?
Well, sorry, yes. So the question is that if you have a trained network, then how do you know whether it's learned or memorized? The practical answer would be to compare the answer, to compare its predictions on data that it has not been trained on. So that would be really the practical answer. But yeah, there could be more theoretical list.
If the network generalizes, then you would say it's learned.
Yes, yes. But that's really just a very practical thing. Yeah, right. So okay. I might have some curves that show you this thing, but if not, they're in the paper. So today, what I'm going to do is trying to use these neural networks to tackle this problem of getting solutions to the Yang Baxter equation. Okay? And of course, the question is that if you're doing data science or machine learning, then what is the data? And essentially, what will turn out is that the data is the fact that the Yang Baxter equation is solved. And so essentially what we're saying is that rather than providing input-output variables, we're going to tell the neural network that, hey, I'm looking for a function, or in this case, a set of functions that together satisfy a complicated nonlinear identity. And again, as we saw, neural networks, you can use them by tuning the weights and biases and their architecture. You can use it to scan across function space without really giving a very explicit ansatz. Like usually if you want to scan across function space, you might take an ansatz of say sines and cosines or what have you, and expand in that complete set of bases. Right? And depending on whether you've chosen a nice enough basis, your expansion would be reasonable. Okay. So, right. But here you don't do that. You just pick an activation function, you pick a width and you pick a depth that defines a neural network. And then you say that, well, I'm scanning across all possible functions that can be reasonably generated by this neural network. And these constraints on the target function are really encoded in something called the loss function. And that's what I'll be coming to. And so here's the loss function. The original idea, which goes back to solving things for Amazon, is you need a metric for evaluating how good or bad is a function at predicting the answer. Right? And for example, you might say that, well, let me compute the mean square error. So the mean square deviation between the actual answer and the predicted answer by the neural network, or really any predictor. Right? And if this is small, then the corresponding predictions are good. And so you might say that, well, that's the framework of canonical supervised learning. You minimize your loss function in your tunable parameters. And conceptually, of course, this is not any different or very different from fitting a straight line through data that you observe. The only difference is that your ansatz, rather than being a straight line, is the set of functions that can be spanned by tuning the parameters of this neural network, right? That's the only difference. So But now what we're going to do is we're going to slightly generalize how we think about these loss functions. And to do that, let's imagine what happens when the loss function is 0, right? So the mean square loss function would only be 0, which is its minimum value kind of by definition. Loss functions are positive semi-definite. So its minimum value would be 0 if all the answers are perfectly reproduced. Okay. So minimizing the loss function is really searching for functions in the set of neural network, in the set of functions spanned by the neural network, such that these set of constraints are true. So what you could do is that you could imagine that loss functions are essentially objects that impose constraints on the target function being learned by the neural network. Okay. And they are 0 when the constraints are satisfied by definition. So this is a cute rewriting for the mean square error. Let me tell you about a place where it's not really a cute rewriting. It really has to be done. And this is again a very practical solution. So the origins of this problem, they really go back to the problem of signature verification for bank checks, not blank ones. So there are like hundreds of thousands of classes which are customers. So probably I should remind people that checks were things that had to be signed on, and you have to. Okay. So you sign on the check, and the bank matches the check against the signature against its records, and then says that, well, it's really you who signed it, and pays it out. Okay, so the signature really has to be identified to the correct user. Okay, and of course, the problem with supervised learning in this framework is that there are many classes, like about millions of classes, ideally, if your bank is doing well, and only 1 or 2 example signatures for each class. This is the exact opposite of things like doing machine learning with, say, CIFAR 10 or MNIST or whatever, where you have 10 classes and maybe a million such examples. This is really the exact opposite of that. And also, new customers are being added, old customers are leaving all the time. So should you really retrain the classifier for these hundreds of thousands of classes or millions of classes every time this happens? So rather than doing that, this was a beautiful solution which these people figured out. So rather than trying to classify the signatures, what you really need to solve is to compare the signature on record with the signature that's given to you, and ask, are these 2 signatures similar or not? Right? You don't really need to understand to classify it to the right person. You just have to match it to one class, which is your hypothesis, and then say whether it's satisfied or not. Right? That's much simpler. And really, this is rather than, and I'll show you in a moment how this is not really predicting an input-output variable, but it's really giving a constraint on the prediction function. Okay, so no talk on machine learning is complete without a picture of a cat and a dog. So here you are. So the idea is that you draw inspiration from, and this is an idea due to Fei at Stanford, that you draw inspiration from how humans learn. So for example, if you're teaching a toddler that this is a dog and this is a cat, you really have to show a dog or a cat 2 or 3 times, and then they know what is what. Okay, and then and it's also able to say, for example, see a different dog or a different kind of a dog that may not have seen before, and still it's able to understand that it's really a dog or a cat. So of course, so what is really happening here is that the toddler is learning this kind of an equivalence relation, that 1 and 3 are similar, 2 and 4 are similar, but 1 and 3 are not similar to 2 and 4. Right? So, right. And this is really the what these people solved. And what they did was that they trained the neural network not to learn to classify, but to answer this question, that you try to learn a function that represents your data, but the constraint on the function is that if the input variables are similar, then the representation, then the points are close together in representation space. Okay. So, and if they're dissimilar by construction, then they're far apart. And then for inference, you just compute how close 2 signatures are, and then that's your answer. And of course, then you have to decide the threshold of how confident you want to be. So here's the recasting as similarity. You think of, instead of having n elements into k classes, you define this equivalence relationship, and then you say that, well, I really have two classes, similar or different. And then you have n choose two elements organized into two classes. Okay. And then, so here's the loss function which does that. Okay, and this is the usual dot product. So, and again, so the intuition for the loss function, the same thing that you might ask, when is it, as for the mean square error, it's not very different. You just ask, when is it 0? So the embedding must be such that when x1 is similar to x2, so y is equal to 1, then phi w match them close together. So when y is equal to 1, then the target distance is really 0, right? So y is equal to 1, distance must be 0. This term is dropped out. Similarly, when y is equal to 0, this must be far apart. When y is 0, then this thing, the max of this must be 0. Yeah, so the distance must be greater than 1. Okay, so so this is the basic structure, which is kind of the inspiration for what we did. Okay, so this is so let me just summarize for you quickly the first half of the talk, which is why neural networks are so powerful at doing the kind of studies we wanted to do. So they are universal approximators. So as long as you're scanning in the set of neural networks, you can be reasonably sure within shouting distance that you're close to your target function. Yeah. And there's a reasonable way of scanning across this thing. You just keep tuning the weights and biases. Okay? And rather than enumerate input-output pairs, you can also enumerate abstract properties of the neural network. So in this case, we enumerated an abstract property that phi is equal to 0 when points are similar. So is that fine? So now let me just tell you a little bit about quantum integrability, and this is just to set up notation because I'm clearly not the right person to be talking about this. But just by way of notation, we have a periodic spin chain on 3 sides, and the Hilbert space is isomorphic to C2. And the Hamiltonian is the sum of nearest neighbor interactions. So these are the kind of systems we are looking at. So, and like Alessandro covered for us very nicely in the previous talk, these systems are really characterized by an R matrix, which again now obeys some axiomatic properties, right? It's a holomorphic function, and simplified again to difference form. It has a constraint on the derivative, which tells you what the Hamiltonian should be. And higher charges can also be extracted from here, right? So really, it's this abstract-looking equation, which, if you think about, is not very different from that Siamese object that we had earlier. So here's the idea: like construct integrable systems from scratch. What we'd like to do is that we'd like to use the neural networks to scan across the set of R matrices. So we assume that the R matrix is holomorphic. It's local. And at the first pass, let's assume that the target Hamiltonian is known, but we can relax this, and we will relax this. Okay? And then you try and construct the R matrix from the Yang Baxter equation, imposing this as a loss function. Okay? So, and I'll sketch out the details for you in a moment, but I do want to give you the overall framework of what we've done. So, and of course, there are very natural questions that one might want to ask. What if rather than giving a specific target Hamiltonian, you want to explore a family of integrable models, right? So you might want to give a set of constraints that a certain set of algebraic equations on the entries of the Hamiltonian are satisfied, right? You might want to say that, okay, I have a set of integrable systems here. Are there other integrable systems, quote unquote, in the vicinity of the starting point? And well, this is really summarizing the previous two questions. That can you find classes of integrable systems. And now you see neural networks are very promising tools for this, right? They span a large function space. Ideally, they can approximate anything. And of course, and also constraints that you're looking to satisfy, you can supply using loss functions. And I particularly wish to point this thing out because it is not true that neural networks are, say, the only universal approximators. You can build a universal approximator very easily by asking that, okay, here's my test point, literally in this room. Maybe I have a training point which is infinitesimally separated from this test point. I go to that training point and I look at what its target value is. Even that, which is called the k-nearest neighbors algorithm, is a universal approximator. Okay, so this having a universal approximator is nothing quote unquote deep or anything to do with neural networks. There are plenty of them, but it's only neural networks that I'm aware of where you can supply these kind of constraints in such a natural way and scan across functions in such a natural way. Okay. So for example, for k-nearest neighbors, to have a universal approximator, I'd need to know target values. And here, again, to emphasize, I don't know target values. I just know some abstract relations between functions. Okay. So as a concrete example, let's consider a family of integrable models. So the Hamiltonian is given by this equation, and you have these constraints that A1 is A2, or this other equation is satisfied. So A1 plus A2 is B1 plus B2. Okay. And again, you can, and these ABCs are complex numbers in general. And this was, and this again has been solved. The full set of solutions is known for these when the vector space is two-dimensional. So for this particular case, it turns out that this is the set of solutions. Okay, so here we know things very well. In fact, for all, in this case, we know all the distinct cases very well. And what I'd like to do is to go back to these questions. Right? And really, here where we know the answers, I'd like to experiment with this to try and convince you that this is a competitive way of getting these results. Okay, great. So how would you want to construct as a solver? You're trying to solve the Yang Baxter equation, and the R matrix consists of functions, Rij, right? Each of these would be a function. And then there are certain constraints which you can either impose as loss functions or put them into the design of the network. And for various reasons, it turns out that some are better to code into the design of the network and some are better to encode into the loss function. I'm happy to explain further if you like, but I should say that I don't really have any systematic understanding of why which one is better. It's just that this one works. This way that we've done it seemed to work the best. Okay. So what are the constraints it might have? Well, it would be holomorphic over the complex plane. It would at u equal to 0, it reduces to this this matrix, the permutation operator, which is really a statement of locality. And the first derivative is related to the Hamiltonian. And at first pass, let's assume that we are really fixing on some target values of the Hamiltonian and trying to solve. And then, of course, the elephant in the room, it should solve the Yang Baxter equation. So the functions Rij should be fixed from these constraints, right? You have the ansatz, you know which elements are non-zero in the R matrix, and you know that these constraints are true. Right? So, and as I said, partly we'll build this into the neural network architecture, and partly we'll implement this using loss functions. Okay. So here's the strategy. We'll train on the real line, but we'll design the neural network in such a way that it manifestly learns a holomorphic function. So how do we do that? So the first thing would be to construct a holomorphic neuron. So you take a holomorphic activation function So this is one example, which is kind of obvious. This is the example that we actually used in the paper. Then if you have a function of the structure where W's and B's are real, and so is the Z should really be the U. Sorry about that. So it's holomorphic in U by construction. If you continue U, this Z or U into the complex plane, you'll get a holomorphic function. But it's real valued for real inputs. There's no reason why the R matrix should be real valued for real inputs. So we extend it a little bit. So we construct functions and that are sums of these two holomorphically activated neurons, right? A plus IB. So this is holomorphic in U, but without the reality constraint.
So you're putting on U.
Yes.
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 The architecture you're using.
Yes. So this is going into the architecture. So you might ask actually. So thanks for the question. So you might ask that, well, you could train over the entire 2D plane and impose the Riemann-Cauchy equations as the loss function, right? Say that I'll learn a generic set of two-dimensional functions and impose the Riemann-Cauchy equation as equations as loss functions. It doesn't really seem to work. It doesn't work. I mean, we essentially end up getting noise. So you have to be pretty careful in how you do this. So let me also point out for you that one of the problems with the approach or with getting solutions to this is that there is a trivial solution of this sitting around, which is that R is equal to P for all values, right? And just near the, just at H is equal to, at U equal to 0, there's a little wiggle in the neural network, which gives you the right derivative, okay? Because neural networks are so flexible, they can even model something like that up to noise. So what happens is that there are these bunch of fake solutions sitting around and you have to kind of remove them carefully. And that becomes much harder to do if you're trying to impose the RC conditions as loss functions.
Can you approximate any holomorphic function within the basic?
Yes, I think so. Yeah.
So you're assuming that you can approximate a holomorphic function using.
Right. So essentially, the statement is that okay. So you take a holomorphic function, you restrict it to the real line. Okay, that breaks up into real and imaginary parts. So this is the real and imaginary. These are the real and imaginary parts of the holomorphic function when restricted to the real line, but they separately analytically continue into the complex plane. Okay, so is that okay? So we just do that, but now for the R matrix. Okay. So the only thing is that instead of having one such function, which is what typically you kind of imagine a neural network would be, here you might have, say, 32 such functions. Yes. Oh. Well, okay. So in practice, it doesn't really matter because if we use things like ReLU and all as well, it is competitive. It's just that, for aesthetic reasons, we didn't want to say that here's this really weird non-differentiable function, and I'm claiming that it's a holomorphic function in R. It's learning a holomorphic function.
But we did see that.
Yes, I mean, yes, that's true. So in practice, it's slightly more efficient than ReLU, this switch activation.
Yeah, but the way I immediately see.
Yes.
That it was efficient.
Yeah.
Yes.
We present some parts of showing that, and it's consistent across all.
So just for people who couldn't hear, the remark was that in fact, it is true in practice also that swish does outperform the other functions, including tanh, including the non-holomorphic ones that are typically used in machine learning. But again, to emphasize, we're not really training on the complex plane, so we're not really using holomorphic anywhere. So we're just trying to learn a function which we know that no matter what we do by construction, whatever this neural network outputs has to be holomorphic. Okay. So yeah. So again, for the R matrix, instead of having one such function, you have generically, you could have 32. And each of those functions we model through this kind of a neural network. It has 2 layers, not one, because we wanted to really learn. Even in practice, having this extra hidden layer is actually better for learning. And Robert, just to answer your question in this context, you asked about what happens about learning versus memorization. In fact, if we take a single hidden layer, which is enough as a universal approximator, in principle, the system doesn't really train very well. If we have too many hidden layers, again, the system doesn't really train very well. But that's kind of known for multi-layer perceptrons, that beyond a point, adding more than 3 or 4 layers isn't really going to buy much. Okay. Sorry. So, but the entire setup, as I said, is really conceptually no different from that Siamese network. Instead of having one function for the Siamese network, we have 32 functions. That's all. Okay, and so overall, you might say that, what is the structure? Well, you have this line that you're training over, this omega. Your sampling points u and v. From the u and v, you build u minus v. At each of these points, you pass it through the neural network to learn a function r. The function r must satisfy these constraints. So it must obey that r of 0 is equal to p. It must obey that r prime of 0 essentially is equal to h, okay, up to p. Then you take, you look in that subset and you try to solve the Yang Baxter equation. If you wish, you can think of solving of the setup like this. Yes.
So can you say a bit more about why it's the Siamese network? Because like in the Siamese network, essentially classification.
Oh, well, it's a Siamese network in the sense that the loss function is not really local. The loss function is being evaluated over 3 points now, or really two independent points. In the Siamese network as well, the loss function is not, it's evaluated over pairs of points. So I mean, I don't want to push the thing about Siamese very hard, but I do want to push this idea that that you're not really constrained to learning input-output variables. That's why I want to, yeah, so that's all. So also, I've never, yes?
In the previous, what is
Rij is the scalar holomorphic function, which are the matrix elements of the R matrix. So Rij would be this function, this function, this function, this function, and so on. Yes. Okay. So now constraining the Hamiltonian, well, there are 2 ways you could do it. You could say that, well, the Hamiltonian is constrained by value. Like I said so far, you could say that, well, the numbers are just fixed to be whatever they are. Say 0.8, so you give this loss function. But you could also constrain it by condition. You could say that A1 is equal to A2, and then your loss function would be that A1 minus A2, the absolute value of this, would be a loss function. Yes. You could also, and we do this, is that you could demand that this is not equal to 0.8. So for example, if you're in the vicinity of a solution that we found, where your neural network, where your Hamiltonian has this value, you might say that, well, let me look for a solution just in the vicinity of that one where the Hamiltonian is slightly different. If I want to carve out, say, a set of integrable models. So you could try to say that, well, I'm going to penalize the network if some value becomes, say, 0.8 or whatever. So, but in practice, I should say that it's a bit difficult to control. So we use it rather sparingly. We can also impose additional constraints like hermeticity. Okay. So again, let me emphasize this again. Even if you don't really care about solving the Yang Baxter equation in weird ways, the thing that I'd really like you to take away is that as long as you're thinking of a problem where you have a constraint equation for functions that you'd like to satisfy, you don't really have a good basis for expanding functions in, or you don't really have a good idea of what all you should be including in your scan, but you do know what the constraints are and they are relatively easy to write, it might be a good idea to look at a neural network implementation. Yes? So if nothing else, that's the takeaway message from this talk. So again, for definiteness, let's look at the XYZ model. It has two parameters, eta and m. So this is so if you set these target values, then they control the Hamiltonian entries. And then it turns out that you see when you train this network, it very quickly settles down into a scan of into orders of magnitude 10 to the minus 8. So the loss function is really settles down to 10 to the minus 8. So which means that the Yang Baxter equation and all of these extra constraints are really satisfied to this order. Yes. It's so it's literally this equation. You take, yeah. Yeah, so again, so right, exactly. That was what I was saying to Sven, that the loss function is not local. It has to be, so at every training step, at every epoch, we sample for 2 points randomly, 2 sets of points u and v. We construct u minus v. That is the training, and that is the mini batch that we train over. Right. So yeah, so that's why I kind of wanted to show you the Siamese example also.
So what exactly?
This. It's literally that you. Yes. So that's what I was saying, that you sampled across sampled for u and v in omega. That gives you your mini batch. And then this equation evaluated at all points in that mini batch is your loss function. Okay. Okay, great. So now, like we said, that we can actually compare with analytic results because we have them. And it turns out that, again, if you eyeball the resulting curves, it's a very pretty match. I can't even show you the discrepancy. And just to note that there's that same degree of freedom of being able to divide out by one scalar function that Alessandro talked about, which is what we've kind of used to compare things here. So, but if you forget about this legend and you don't really care about what this legend means, but you can really care about the fact that this curve looks so nice. So each of these curves is really 2 curves sitting on top of each other. So this gives us at least some hope that we are not doing completely insane things. Okay, good. So now let's try to look at how to carve out the landscape of integrable models. So here's a thought experiment. Supposing somebody told you that there's an XXZ model. This is a class of models that is completely known. Okay, then you might say that, okay, can you discover that by starting from XXZ, can you navigate away from XXZ models and discover that there's actually an XYZ class of, that this is really a special case of XYZ. So, and of course, again, XXZ is m is equal to 0 in the XYZ case. And again, I should emphasize that this is so pretty because we really know the answer. And I'll shortly show you a plot where we don't know the answer and it's not so pretty. But here's the framework. So you train to XXZ for some number of epochs until you have a reasonable answer. Then again, so this is again for prettiness. We deform eta away. So again, so we have 3 XXZ models at the end of the pre-training, which are our starting points. Then what we do is that we randomly sample some non-zero values of m and train for some small number of epochs, and we do converge to the correct XXZ models. And in fact, if you want to look at how the loss functions evolve, so here are the loss functions for, say, the Yang Baxter equation and the Hamiltonian. So you see they fall quite nicely, and then when you kick away to the new XXZ cases, then again they spike up a bit, but then again they kind of kind of equilibrate to reasonable values. And again, so the spikes correspond to resetting the target Hamiltonian values over here. Right? So, so here's the second experiment I'd like to show you, which is exploring 6 vertex models. Right? So here's the set of models that I wrote down the answers for. And they fall into these 2 classes. So, and the aim of this experiment is to try and discover these 2 classes. So here's the strategy. So you start out by some integrable Hamiltonian, and then you repel away from it by penalizing these the Hamiltonian condition. This is that repulsive condition that I talked about earlier. And then having done that, you again optimize, but now you optimize only over the Yang Baxter loss and locality. So essentially what you're saying is that you train to one such starting point, and then you navigate away from that by a very low, by doing a very small training, so that you can expect that you still stay in that little submanifold of integrable models. So that's the idea of how to explore this landscape. So that's why in the final step, we don't really give a target Hamiltonian. We just say that we just train again, but only over the Yang Baxter loss and locality. And if you do that, then again, you find that there are these little kicks where you navigate away from the solution. But again, but after you've navigated away by using this repulsion, then again, the solution converges very nicely into integrable models. And again, to emphasize this, this is 10 to the minus 4. This was really just, we were running things with very limited computational resources. But again, to emphasize this, that here we know the answer, so we can be quite confident that each of these really is an integrable model. And we would converge to the correct answers, to the same loss values as before if we trained for longer. That's fine. So if you want to visualize the set of Hamiltonians that's been collected in this way, they really do seem to fall into 2 classes. Okay. There is a little bit of post hoc ergo propter hoc going on here, that I know that I should be finding these 2 classes. So I've kind of basically tortured the data until I've got them. But again, I mean, in settings where things are a bit controlled, it really does look like this is a promising approach. So yeah, so these are 6 vertex models. So this would be taking 1, 2, 3, 4, 5, 6 complex dimensions. So the Hamiltonian values, those 6 complex numbers, and then doing dimensional reduction to 2 dimensions. And we do find these 2 clusters. Okay. And if you want to visualize, again, the learned Hamiltonians in a basis where you know what the answers are, so you do find that they fall exactly where they should be. Yes?
So did you try also these?
Yeah, I mean, they all work up to a particular point and they stop working after that. So the fact that I use t-SNE is really just taste. I mean, this works a little bit better. PCA doesn't work that well. Yeah.
But so the question was in the direction that we cover actually next level.
Right, right. Yeah, yeah. PCA doesn't seem to give. So okay, well, we are done. So here's the summary of the talk, and then I'll just show you a little bit. One more slide. So if nothing else, please take away the fact that neural networks are universal approximators. If you want to take away a little bit more, you can. They're very intuitive for finding functions that obey certain constraints rather than actual target values. Okay. Want to take away a bit more about our work? Well, these 3 points. You can solve the Yang Baxter equation, at least in settings where we have control, and we can exhaustively recover some solutions. We can develop strategies that we are now using. And well, this is what we are doing right now. We are trying to make sense of how to get analytic solutions from this approach, finding new solutions, and well, many more things, which owe to the fact that universal approximators, abstract constraints. Okay, just as a little teaser for you, this is really just a teaser. We are trying to make much sense of this, so I don't have much to say about this. But yeah, so if you let the Hilbert space, instead of being isomorphic to C2, you let it be C3. The R matrix is now 9 cross 9, so 81 functions rather than 45, rather than 16. But really, the structure, the framework, and all it's all the same. Instead of taking a two-dimensional vector space, you're taking a three-dimensional one. So pretty much most of the things go through. Computationally, it's much more much more intensive. But other than that, there's no other problem. And what we seem to find is that if we let the code run wild, in the sense of this explorer that I talked about here, then the results seem to fall into two independent two classes, one with 21 complex functions and the other with 36. What these are, how to make sense of them, this is all in progress right now, so I don't really have much to say about that. So that's all for today. So thank you for your time.
Further questions?
Nice talk. I wanted to ask you, what were the errors that you found for when comparing your numerical results with the actual known results for the entrance? Sorry?
The errors?
Yes.
Yes. So it's really a question of taste and how long you're willing to make your computer suffer. If you run it for a relatively short number of epochs, you get about 10 to the minus 4.
I know, but I don't mean the laws. The errors in the Hamiltonians, for instance.
The errors in the Hamiltonians. So, well, if you wish, I didn't really have these down here, but again, about 10 to the minus 3, if you step
okay.
slide. Yeah?
Okay. Okay.
So they're all roughly the same order of magnitude. In fact, if I show you xxz, where again we trained with the actual target value. So this is if you want to prototype, this is a kind of computation where you're very sure that there's an integrable Hamiltonian, and you want to find it. Then you can even train down to 10 to the minus 8. Even the Hamiltonian is accurate up to that point.
Okay, and also since you were considering holomorphic properties in your neural network,
yes,
could you consider also adding weights and biases as complex numbers?
Yes, the training is kind of harder to control. It's harder to control. Essentially, so I'm far from an expert. Maybe Robert has comments, but the point is that if you have complex weights and biases, in principle, you can of course set up such a thing, but to control it using gradient descent is a bit iffy. So what essentially what one is reduced to is, say, using polynomial activations. So, and again, that's harder to control, because if you want to add layers, then if your activation is, say, z square or z cube or z4, then imagine that your error is also of that order. So your gradient descent steps and all, everything becomes harder to control. And this is just keeping aside even the complication of having poles and all. So I think there are more comments about that. Sven.
Yeah, I agree with what you said. So my question is on you start with a relatively biased version of the network, so that is very close to the R matrix effectively. So a lot of the time, I mean, you have basically all this, you know the analytic formula, right?
Well, so
maybe you show it. Let's go back to the slide and see.
Well, yes and no. So the only thing that that in principle one needs to use to find these models is to know which functions to turn on over here. So that's the only place where I've cheated. But even that's not necessary, really. That cheat is also to make sure that I'm not, exploring essentially the same gauge transformed version of the same Hamiltonian.
Yeah. So my question is in terms of how far can you push symbolic regression on the answers? So because you have this trade-off, right, between biasing your network into the right structure versus having it too general and it won't learn?
Well, I'm not sure this is an issue of bias in the network.
So if you go back to the slide where you have the analytic expression, then I can make that precise. Yeah.
Yes.
Yeah, exactly. So you see that's that structure. So in some sense, are you able to recover, say, the e to the bu cos u plus sinh u?
In some cases, yes, but that's again very partial and very preliminary. So
Okay.
some functions one can actually recover, but it really you have to squint at it the right way and all. So that's why these are things that I've kind of like skated over on purpose. So you do, so symbolic regression does work, but it also, it's kind of complicated by the kind of functions that your regressor is using in its basis and stuff. So we're trying to work around this, but so for example, another set of experiments I ran could be that, well, at least functions like this are easy to spot by the regressor. Okay, so you could say that, well, now I know this function, so I plug that in as a known function into the R matrix, and I train for the other unknowns, right? It doesn't really seem to help that much, but also, I should say that at this point, I'm also not sure whether it's an issue of simple numerical precision, because by default, these things are in 32-bit.
No. So the idea was, in some sense, you learn your network, and
Yes.
then later you use symbolic regression to fit
Yes.
it.
Yes.
Right? So in that sense,
In a
but you say
perfect-
basically you have to, as soon as you make too many as you make your bases too large, it becomes hard.
Well, no. Yeah, actually, let me hold off on saying things about symbolic regression for the moment.
Okay.
Yeah. It's
Sorry.
no worries.
We have further questions? In that case, let's thank our speaker again.